section 8.6, we're going to talk about energy, particularly the rotational kinetic energy. Remember, kinetic energy is associated with motion. So in the translational case, what was our formula for kinetic energy? 1/2 mv squared, where v is the translational velocity. But if you also have rotational motion, then there's an energy associated with that motion. And that, by analogy, is going to be 1/2. The equivalent to m was moment of inertia, I. Equivalent of v is our angular velocity, omega. So 1/2 I omega squared. Yeah? Let's just write down the kinetic energy for translation so that you have it there. Kinetic energy for translation, it was 1/2 mv squared. And we just wrote these by analogy, right? Okay. So sometimes it can be quite useful to think in terms of energies to solve a problem, and the problem gets simplified. Remember, we did the work energy theorem in chapter 5, which said that if you have non-conservative forces, that means frictional forces, yeah, so you need to do work against them, and the work needs to come from the difference in energy between your starting energy and your final energy. So some energy has to be expended to do the work. So that's the change in kinetic energy and plus the change in potential energy. Now the kinetic energy could be translational, could also be rotational. So we've included this rotational term here. Okay, this is the new term that we included because we're now considering rotation as well as translation. Okay. If you don't have any non-conservative forces, then your delta change in energy will be 0. Okay, that means your total initial energy equals your total final energy. What are the parts of your total initial energy? There may be kinetic, there may be potential due to gravity, there may be potential due to spring. In this case, we're not considering a spring, so we didn't write that in here. But if there was, you would add that too. Okay. So you need to know conservative and non-conservative forces very well. Okay. In general, solving energy-based problems exactly like you did in chapter 4. You consider 2 points of interest. At one position, everything will be given to you. Another position is where you want to know some information about. And you're going to see whether all your forces are conservative or non-conservative to decide which equation to use. Then you're going to use that equation, put in the known values, and try to solve for the unknown. When you're doing this, you might need to have a relationship between the linear terms and the angular terms. So you can use any of those 3 relationships, right? The most common one that's needed is B equals R omega, but you also have other ones where X equals R theta and A equals R alpha. Yeah, you should know these.